All right, so let's work through an example to see the integral test in action. So consider this series here. We've got the sum from n equals 1 to infinity of 1 over the quantity 2n plus 3 squared. And the question is, does this series converge or diverge? So to use the integral test here, what we're going to do is we're going to take the expression for the term of our series, and we're going to simply replace n with x to cook ourselves up a function. And now, in order to apply the integral test, we need to make sure that this function has three properties. This function needs to be decreasing, a downhill graph, positive, north of the x-axis graph, continuous, a graph that lacks a hole, a jump, or a vertical asymptote. So we can note each of these things. Note the function is going to be decreasing, in fact, because the larger x gets, the larger the denominator of this fraction gets, and as a result, the fraction values are going to be getting smaller as x gets larger. So this function is indeed going to have a downhill graph. If you don't believe the justification that was just outlaid, you could throw this graph or this function rather into your graphing calculator and get a picture to sort of confirm that to yourself. I also claim that this function is positive. Note, no matter what x we're plugging in here, we're looking at the interval between 1 and infinity. We're plugging in positive x values, and positive x values times 2 plus 3, still positive. Square a positive thing, you get a positive thing. So this fraction is always 1 over a positive thing, which yields a positive thing as a result. So this function yields positive values. This function's graph would live north of the x-axis. If you don't believe that as well, you could take this function and throw it in your graphing calculator and supply some evidence to yourself for that. In addition, I claim this function is continuous. Well, in particular, continuous on our interval of interest, because we are interested between 1 and infinity. And yes, while this function has a vertical asymptote at negative 1/2, it does not, or excuse me, negative 1.5. It does not have a lack of continuity anywhere on our interval. So if you plug in a number between 1 and infinity for x, you're always going to get something that's a good old-fashioned number off the number line out of your function, and as a result, this function will be hole-free, jump-free, asymptote-free, regardless of the value of x on our interval of interest. So since our function is decreasing, positive, and continuous, we can apply the integral test. So how do you apply the integral test? Well, you essentially take the series as it is written, and you replace the sigma with an integral sign, replace the n with x. So we take our function that we've got, our f of x, and we simply look at an integral now between 1 and infinity of our function in terms of x. Now, of course, this is an improper integral because we've got an infinite bound, so what do? We take a limit as t goes to infinity of 1 over t, integral from 1 to t of 1 over 2x plus 3 squared dx. Okay, so now, how are we going to approach this limit? I'm going to take this in two stages. So the first stage is just going to deal with the actual antiderivative function itself, and then the second stage is to actually work through the limit. So as our first step of the game here, let's just actually figure out what the capital F function is for this given function. So if we take the integral of 2x plus 3 squared in the denominator, all under 1 in a fraction, we could use u substitution on this. So if we let u be 2x plus 3, then of course du, take the derivative, just 2 dx. And applying the substitution here, let's see, to get dx substituted in, you'd have to divide by 2. So you get 1/2 du is equal to dx. And then the function itself would become 1 over u squared. Now, of course, 1 over u squared is easier to integrate if we simply rewrite it as u to the minus 2. So having done that, then we can apply the power rule, increase the power by 1, put the power in front. Long story short, we'll get minus 1/2 u to the minus 1 plus c as our antiderivative function. And for the sake of computational simplicity, because note, we're going to have to be plugging in values of 1 and t later, I'm just going to bring that u to the minus 1 downstairs as 1 power of u in the denominator for simplicity's sake, because it's going to be easier to plug and chug and see what's going on when we've got our positive power of u. So here we are, we've got our antiderivative function. It's negative 1 over 2u plus c. Now, we are not just looking at the antiderivative function, we are actually going to be looking at this within a definite integral. So we're going to be plugging in values for 1 and t. So the c is ultimately going to cancel whenever we would take the difference of those two antiderivative evaluations. And moreover, the u is going to be replaced by 2x plus 3, because this 1 and this 2 came off of the x-axis. So we're going to need to be plugging in values in for x with 1 and t. So if we take our antiderivative function and rewrite it as negative 1 over 2 times whatever u is, namely 2x plus 3, we would have ourselves the antiderivative function that is associated with our original integral of interest. So we have our antiderivative function, and now we're simply evaluating at t and 1. So we evaluate at t, we evaluate at 1, and we subtract. Evaluating at t is pretty simple, just plug in t for x. Evaluating at 1, note inside the parenthesis you get a 5 when you evaluate at 1. So ultimately our expression comes out to be what it is as written here. Now we're taking a limit as t goes to infinity. So ultimately this denominator of this fraction is getting very big. And as the denominator gets very big, the fraction value goes to 0. And as a result then, the only thing that's left is this 1 over 2 times 5, which evaluates to 1/10. Now that means that the area under this function, 1 over 2x cubed quantity squared, from 1 to infinity, has an area of 1/10. What that means is that the integral that was associated with our original series converged. And if you recall from the results of the integral test, if your integral converges, then your series converges. So a summative statement to sort of put it all together here. Since our integral from 1 to infinity converges, our series from 1 to infinity converges by the integral test. Now, I want to make one note about this because if you notice when we computed the area under our function, we got 1/10, right? Let me just make a note on this. This is the area under our function f of x on the interval 1 comma infinity. I want to make a remark here because this area, while very meaningful when it comes to the integral test, this area only tells us that the series also has finite value for its sum. I claim it does not tell us that the sum adds to infinity. So to be clear, let me pull back some information that we had previously looked at, and this is whenever we're determining when we were determining that the integral test even made logical sense. And in the case of convergence, what we noticed was if the area under the function, namely the black area, was just a finite number, then the sum of the areas of all of the bar graphs, the bars in the bar graph, also came out to be a finite value, which was cool, which was great. But see, what we've shown here is that the area of f of x is 1/10. Well, that's the area analogously to our picture. That's the area that we're seeing here. Now, is the fact that the area under the function is 1/10, does that tell you that the area of all the bar graphs, of all the bars of the graph added together is 1/10? No, it doesn't. So the one thing I want to just make a note of here, just so that we're all on the same page, is note the sum n equals 1 to infinity of 1 over 2n plus 3 squared does not equal 10. We are not saying that the area of all of the bars in the bar graph equals 10. Oh, let me get that up on the page so that you can see that. Okay, we are not saying that the sum of the areas of all of the bars in the bar graph equals 10. No, the fact that the integral evaluated to 1/10 means that the area under the function is 1/10. So we can't ultimately conclude anything about what the precise value of our series is. However, what we can say is because, and this is still very important, because the integral associated with our series converge, in other words, had a finite value, then we can also say that our series would have a finite value. And that alone is actually what was asked of us, right? Because if we scroll back to where the problem originally started, we were trying to determine if the series converged or diverged, and in fact, we have determined precisely this.